All right, geometry class. Happy snow day, e-learning day. We are going to take a look at lesson 9.4. And your assignment from today or for today is going to also be based on symmetry. Most of you probably think of symmetry as something as simple as taking a butterfly or a shape that you learned in elementary school and potentially cutting it in half. So if I had like a butterfly drawn right here, excuse my drawing, but something like this, and I asked you to draw lines of symmetry, I believe in elementary school, you probably said, okay, we have to cut this butterfly right in half, and that would be a line of symmetry. That is one type of symmetry we're going to talk about, but we're really going to focus on two other types in lesson 9.4. So a figure has symmetry. The technical definition of symmetry is that a figure has symmetry if an isometry, which is a transformation we've been talking about, can map a figure onto itself. So in order to show you kind of what this definition is talking about, I'm going to look at the capital letter H. If I look at the capital letter H, there is a transformation that's going to take and map this onto itself. So for example, if I use this as a line of reflection, and I took and I reflected this part of the H right here over that line of reflection to here, that is going to exactly map directly on top of itself, which makes this figure have symmetry. So obviously reflection is one way to have symmetry. And the next couple of slides we'll look at other isometries that do, in a sense, the same thing. So anytime you can do, basically what it's going to be limited to is a rotation, excuse me, a rotation or a reflection, then the object has symmetry. So either rotate or reflect. This one right here is one you're very comfortable with. The rotation one is one we're going to spend most of the time talking about today. So continuing to the next slide. Line symmetry is the one you're most comfortable with. Line symmetry is the same as reflectional symmetry. So anytime you're asked to find basically lines of symmetry, we're going to really just be looking for reflection lines. So line symmetry is the same as reflectional symmetry, and I really don't care which word you choose to use whatever one makes the most sense. So these two are completely interchangeable. And when we drew that capital letter H on the last page, that was an example of reflectional symmetry. Another example of reflectional symmetry would be the capital letter C. If I take the capital letter C and reflect again across this line right here, you'll see that this portion of the C up here is going to map or reflect directly onto itself down here. So hence this has both reflectional and or line symmetry. Some shapes might have more than one line of symmetry when talking about reflectional symmetry. We'll see that later on. Here's an example of a heart. This heart definitely has a line of symmetry as shown with the dotted line. But it also could be said to have reflectional symmetry, which again is the same as line symmetry. This slide right here is the most important by far to tune into at home. A figure has rotational symmetry if the figure can be rotated onto itself for some rotation of 180 degrees or less. So we have to be less than 180 degrees or it's not considered rotational symmetry. So let me explain again. I'm going to maybe use a rectangle, for example, just because it's easy for me to rotate. If I take this rectangle and draw a point directly in the middle of it, and I trace over this rectangle, oops, sorry, wrong tool here. If I trace over this rectangle, I can demonstrate rotational symmetry. So if I take this shape and rotate it 180 degrees, this right here would be 90 degrees. Actually, technically, we should be going this way. Positive rotation is this way. It doesn't really matter which direction you go, but just to be clear, this is going to be positive 90 degrees, and then this would be 180 degrees, and we're right back to itself. So this has rotational symmetry because it could be rotated in 180 degrees or less. If you have to rotate more than 180 degrees, the shape does not have rotational symmetry. So anytime your rotation is greater than 180, rotational symmetry does not occur. Here's why. If I took this crazy shape right here and I asked, is this shape symmetric? The answer is definitely no. But if you were using the argument of rotational symmetry, you could say, well, in a sense, you could rotate this a full 180 degrees, it'd be upside down. But if you rotate 360, it's going to get back to itself. So rotating 360 degrees is not a relevant form of rotational symmetry. And I guess that's, in a sense, why you have to be less than or equal to 180 degrees. We'll look at more examples here shortly. A figure has point symmetry if its rotational symmetry is exactly 180 degrees. So if we're looking at the examples I just did right here, this figure has both rotational symmetry and point symmetry. The reason it has rotational symmetry is because it could be rotated 180 degrees or less, and it has point symmetry because it equals exactly 180 degrees in order to do so. So anytime your rotational symmetry equals 180, then it's also considered point symmetry. So we'll look at some examples here of objects that have rotational symmetry as well as point symmetry and ones that don't. So on the next slide, we're going to kind of reinvestigate or look at this a little bit closer. If I take this object right here and rotate a full 180 degrees, 180 degrees is going to mean that this point up here is going to end up down here. So 180 degrees would be going from here to here. If I take this object and rotate that point down here, you'll notice that it does not match up to itself. So this figure, 180 degrees, which does not work for point symmetry. So this particular pentagon would not have point symmetry. It fails. However, if I go back and look at this a little bit closer, we could take this pentagon and I could say, okay, well, I know that the rotational symmetry of 180 didn't work, but if I start by tracing over this object and rotating it only this far, the object does map onto itself. And that rotation is going to be less than 180, so it does have rotational symmetry. If I end up taking this point and simply rotating it from here to here, we do have rotational symmetry. So rotational symmetry does work. If we wanted to figure out degrees for rotational symmetry, we're going to take that full rotation, which is 360, and we're just going to divide that by 5, because there's 5 sides. So 360 divided by 5 equals 72 degrees. So 72 degrees would be one rotational symmetry. We can also add another 72 degrees and have rotational symmetry of 144 degrees as well, because that is also less than 180. So this has rotational symmetry of 144 and 72 degrees, both. However, it does not have point symmetry because 180 degrees, once again, did not work. So here's a figure right here. It's easier for me, obviously, with technology to take a look at this. I wouldn't recognize this as any particular shape, But if we want to check to see if this does have point or rotational symmetry, we can go ahead and rotate. So if I grab a hold of this shape right here and I rotate, this would be 90 degrees. It does not match up. This would be 180. And when I get back to 180 degrees, we map this directly back onto itself. So it says the figure is its own image after a half turn, and a half turn is 180 degrees. So it has rotational symmetry with a 180-degree angle. Because that is specifically or exactly 180, this figure also has point symmetry. So here would be an example of an object that has both point symmetry and rotational symmetry. This object does not have line symmetry. Identifying lines of symmetry, draw all lines of symmetry. This is kind of going back to the reflectional symmetry piece. Obviously, this line of symmetry vertically right through the middle is going to map this side onto this side. One common mistake I often see is students start to think diagonals are the same as symmetry. So they'll draw that red line and this red line for lines of symmetry. Those do not work. Those are not lines of symmetry. If I go back and just delete this, I can show you. If I took this part of the trapezoid and mapped it, it's actually going to end up being something like this if it was reflected. And you can see that that reflection does not work. So this line of symmetry or that diagonal fails, whereas this moving from here over to here does work. So that one checks out. Judging from appearance, do the letters V and H have rotational symmetry? If so, what is the angle of rotation? So starting with the letter V, if I take this shape and look to trace it, you will see that in order to get this back to itself, I have to go more than 90, more than 180, more than 270, all the way back to 360 degrees. So the letter V does not have rotational symmetry because it must be rotated 360 degrees of full rotation before it matches back to itself. Back to the letter H, we already talked about a little bit with reflectional symmetry. But if I take the letter H and once again trace over it just for viewing purposes, and I rotate this letter H, we can see that after 90, we're not back on top of itself. After 180, we are right back to the original image. So this particular letter does have both rotational and point symmetry. So we could say that yes, the letter H does have rotational symmetry. It also has point symmetry as well. Draw a rectangle and all lines of symmetry. We're going to go ahead and take a look at this. We're just about through this lesson. Again, the very obvious lines of symmetry in this particular shape are the vertical line right through the middle and the horizontal line straight through the middle here. Common mistakes I see will be that students will draw a line from corner to corner and corner to corner and say that those are also lines of symmetry. Similar to the trapezoid we looked at, if I took this rectangle and folded this shaded region right here onto itself using a reflection, we would actually end up with a shape much like this, and you can see that that's not going to map onto itself. So these two black horizontal and vertical lines are okay, and once again these diagonals fail. So please do be careful with that. Okay, so last slide is looking at this crazy shape over here. It says, does this particular object have rotational symmetry? So what we need to do is we need to visualize what would happen if we start rotating this object about its center of mass or center. So if I take this shape and I rotate it 90 or to here, that is not mapped onto itself. However, if I go to 180, we are right back to itself. So this object does indeed have rotational symmetry. Oops. And it says, if so, give the angle of rotation. So you would say yes, It has rotational symmetry of 180 degrees. Does the figure have point symmetry? Well, also, yes. And your answer is going to be because it's exactly 180 degrees. So because the rotational was exactly 180 degrees, then the object does have point symmetry. So I really want to connect those two pieces right there, that they are separate, but this is just more specific as to the type of rotational symmetry. So hopefully that gives you a little better idea. If you look at your assignment, your task is actually to go outside, grab a shovel, find some snow, and shovel a picture of 3 separate objects with point, line, and rotational symmetry. So, for example, if this is my front yard, big snowy field right here, I'm going to go outside and I'm going to shovel out some shapes. So I might take the shovel and remove something like this. Again, don't judge my drawing. I'm just trying to give you some ideas here of what you could do. Hopefully you're not copying my examples and finding something unique. So I might shovel out an M for Mueller and then lay a stick or draw a line or whatever across this and take a picture of it. Once I get the picture uploaded, I would say that this has reflectional symmetry. Okay, I would then have to find another object that has rotational symmetry. So maybe for rotational symmetry, I decide that I'm gonna, I have no idea, draw in the snow some crosshairs. And this definitely has rotational symmetry because if I rotate this 90 degrees or 180 degrees, this has rotational symmetry. So I take a picture of it and upload it to the same document. And last but not least, I need something with point symmetry or some object that has point symmetry. So maybe you want to get really creative and you want to draw the Under Armour logo in the snow. If you take this object and rotate it, again, exactly 180 degrees, then this object would have point symmetry. It does map back to itself. Excuse my drawing. So this object would have point symmetry. So all I would have to do is write point symmetry. After you take the picture, you can just type that into the document and upload it. Once you get all these 3 compiled into one Google Doc, after you've taken your pictures, upload it to Classroom, and you are done for the day. Get creative. I'll give some serious extra credit to the best. 3 examples of these that are done neatly and detailed in the snow. Good luck.